Hi, myself as Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we will have a look on question bank discussion on multiprocessors. So, multiprocessor means a system which consists of multiple processors. That is called multiprocessor system. So, in so the first question is explain about the arithmetic pipeline. So pipelining means executing two or more instructions simultaneously. That is called pipelining. So by using the pipelining concept, we can enhance the performance of the computer. So that is a main advantage with the pipelining technique. So we are discussing the arithmetic pipeline. So these arithmetic pipeline units are usually found in very high speed computers. So especially these arithmetic pipelines we are using where the higher speed is required. So there we can use this pipeline arithmetic units. So the arithmetic pipelines are constructed especially for simple fixed point operations and floating point arithmetic operations. So this arithmetic pipeline, it is constructed for these two. One is the simple fixed point operations, and the second one is a floating point arithmetic operations. So to understand these concepts of arithmetic pipeline in a more convenient way, let us consider an example of pipeline unit for floating point addition and subtraction. So by taking this floating point addition and subtraction, then we can see how the arithmetic pipeline will take place. So the inputs to the pipelining adder pipeline are two normalized floating point binary numbers. So this we are assuming these two are the normalized floating point numbers. So basically, the floating points in a scientific notation we can write like this. So x is equal to a into 10 power a. So where a is the mantissa and small a is the it is a exponent. And similarly, the second number is the b into 10 power small b. So where this capital B is the it is a mantissa of the second number, and small b is the exponent of the second number. So in this way we can represent any floating point number. So using the mantissa and the base mantissa base and exponent. So the combined operation of floating point addition and subtraction, it is divided into four segments. So in this, especially here, we are discussing about floating point addition and subtraction. So entire this floating point addition and subtraction operations, we are dividing into four segments. We are dividing into four segments. So each segment, it contains the corresponding sub operation to be performed in a given pipeline. So the sub operations are these are the four sub operations that are performed in the four segments. So the first one is the compare the exponents by subtraction, then align the mantissas. Third one, add or subtract the mantissas. Then finally, we have to normalize the result. So this is a process how the floating point of the addition and subtraction takes place. So this is a block diagram. It represents the various sub operations performed in each segment of the pipeline. So already we know. So total we have four segments: segment 1, segment 2, segment 3, segment 4. So in segment 1, we performing or we are comparing the exponents by the subtraction. In segment 2, we are performing the alignment of the mantissas. In segment 3, we are performing addition or subtraction of the mantissas. And in segment 4, we are performing normalizing the result. So these are the various operations that are performed in the various segments. So see, we have two numbers, two floating point numbers. So their mantices are capital A and capital B. So the capital A and capital B are the mantices of the two floating point numbers, and the small a, small b are the exponents of the two floating point numbers. So the first operation is a compare the exponents by subtraction. So in order to perform addition or subtraction, the exponents should be same. But when the exponents are, we are checking whether the exponents are same or not by comparing the exponents. Okay, so comparison is nothing but we are performing the subtraction. Okay, so we are comparing the exponents by subtraction, and if there is any, if their exponents are uh, not equal, then we are aligning the mantices. We are aligning the mantices, and then we are performing addition or subtraction of the mantices. Then we are normalizing the result. So suppose if their exponents are similar, then we are choosing the larger exponent as the result of the exponent of the result, then adjust the exponent, then finally the operation will be performed. Okay, so we can better understand with a example. So the first one is the compare exponents by subtraction. So we have two numbers, x and y. So x value is 0.9200 into 10 power 3, and the another number is y is equal to 0.8304 into 10 power 2. So here the exponents are not same. Exponents are not equal. So that means the difference is 3 minus 2, that is equal to 1. So one difference is there. One difference is there in their exponents. So the second operation is align the mantices. Align the mantices. So the mantissa associated with the smaller exponent is shifted according to the difference of the exponents determined in segment 1. So the difference is 1. So we have to choose the number with the smaller exponent. So the smaller exponent is the second number, and we have to align the mantissa. So see here. So this we are writing in terms of 10 power 3. So 10 power 3. So how we will get the 10 power 3? So we will increase the exponent if we perform shift right operation. So if we perform shift right operation, this number it becomes 0.0830 into 10 power 4. 10 power, okay, so already it is 3, so that it will become 10 power 3. So this is a after performing alignment of the mantissa. So now the x value will be x is equal to 0.9200 into 10 power 3, and y value will be y is equal to 0.0830 into 10 power 3. So now the exponents are equal. Now we are performing addition or subtraction. Okay. So once you perform addition, then the value 1.0030 into 10 power 3. Similarly, if you perform subtraction, you will get 0.8370 into 10 power 3. Okay. So after performing addition or subtraction, then we need to check whether the result is in the normalized result or not. So normalized result means after writing a floating point number, C. So in general, we will write like something 1.98 into 10 power 3. So that means it is a decimal point. So if we have a non-zero value before the decimal number, and this non-zero value should not follow any following zeros, so then it is said to be normalized. Normalized. Suppose if I have a 0 before the decimal point, like 0. 8543 into 10 power 3. So here it is a not normalized. It is a unnormalized, not normalized result. Because here before the decimal point we have a 0. So that is not the case. So this is a not normalized. So the condition for normalized is before the decimal point we should have a non-zero value, and that non-zero value should not have should not followed by the zeros. So this is a normalized. So the addition is it is already in the normalized form, because we have before the decimal point we have a non-zero value, and if you see the result of the subtraction, it is in the form of 0.8370 into 10 power 3. So it is not in the normalized result. So it has to be converted into the normalized. So we have to decide whether how we can get it to the normalized result. So if I want to make before the decimal point is a non-zero value, I need to perform shift left. Shift left. So if I perform shift left, I will one bit, then I will get 8.3700 into 10 power 2. Because if I perform one bit shift left, the 8 will comes to here, then 3 will comes to here. So in this way, all the digits will be one bit moved towards the left side, and their exponent. So if we perform shift left operation, their exponent will be decremented by 1, and if we perform right shift right, then exponent will be incremented by 1. So 3 becomes 2. So it is a normalized, because before the decimal point we have a non-zero, and that non-zero value is not following any leading zeros. So this is a normalized. So in this way we can perform arithmetic floating point addition and subtraction. Next one, explain the flowchart of 4-segment instruction pipeline with a neat sketch. What are the conflicts that occur during instruction pipeline? So already we have seen what is pipelining. Pipelining means executing 2 or more instructions simultaneously. That is called pipelining. So in pipelining, the instruction should follow some sequence of steps. Okay, so that are, see, first one is the fetch the instruction from the memory. Fetching is nothing but retrieving the instruction from the memory, because we are storing our program in the memory. So from the memory, the instructions will be retrieved. So that is the first step. Then decode the instruction. So decode in the sense it will interpret the operation, what type of operation it has to perform, whether it is a addition, subtraction, multiplication, division, increment, or once it is decoded, then it calculates the effective address if it is having indirect addressing mode. Then fetching the operand from the memory, then operand is fetching from the memory, then execute that instruction. Execution is nothing but implementing those operations. Suppose if it is addition, then in the execution phase the addition operation will be performed. Then after performing we will get the result. So then storing the result in the proper place, that means we can store the result whether it is a register inside the register, or you can also store in the memory. So these are the various sequence of operations that are performed by every instruction. So all these operations we are dividing into 4 segments by combining some of the operations. So the first segment is a fetch instruction from the memory. So this is the first phase. Then next, the second and third, these 2 operations by combining it will form a segment 2. So segment 2 is a decode the instruction and calculate the effective address. Then fetch the operand from the memory. So that is a segment 3. And in segment 4, execute the instruction and store the result in a a proper place. So by combining fifth and sixth, it will form a segment 4. So this is a segment 4. Execute the instruction. Okay. So the pipeline may not perform at its maximum rate due to different segments taking different times to operate. So this is a flowchart how all these operations will be performed in various segments. Segment 1, 2, 3, 4. So this is a 4 segment pipeline structure. So after decoding, if we are checking whether is there any branching instruction. Branching means transferring program control from one address to the new address. Instead of going to the next address, it is going to some new address. That is called branching. So if the branching is occurred, then the next step is it has to update the program counter. Then it will empty the pipeline. That means a new instruction will be fetched from the memory. Okay. Okay. Suppose after executing the instruction, then if there is any interrupt occurred, so interrupt is nothing but something which breaks the routine. So if any interrupt is occurred, then it will the corresponding interrupt handling operation will be performed. Then it will update the PC, then it will empty the pipeline. So again the next instruction will be fetched from the memory. So similarly, if there no interrupt, then a new instruction will be fetched from the memory. So this is a flowchart for a 4-segment pipeline mechanism. So here you can see and the entire 6 operations we are dividing into 4 segments. First one is fetching the instruction, that is represented with Fi. Second one, decoding the instruction, DA. And third one is fetching the operand. And last one is executing the instruction. So these are the 4 segments: Fi, DA, FO, EX. So let's see. So these are the instructions of the program. So program consists of several instructions. So the first instruction, it fetching from the memory. After fetching, then it will be decoded. So in the second clock cycle, so these are the clock cycles: first clock cycle, second, third, fourth, up to the 13 clock cycles. So during the second clock cycle, the first instruction is decoding. So while the first instruction is in decoding phase, the second instruction I2 it is fetched from the memory. Similarly, while the first instruction is in the phase of fetching the operand, the second instruction is in the phase of decoding. While the first instruction is in the execution phase, the second instruction will be fetched the operand from the memory. So that means by the 5th clock cycle, the first instruction will be first instruction execution will be completed. Then the second instruction execution will be takes place. So that means here at 4th clock cycle, it is observed that all the various operations are takes place parallelly. That means the first instruction is executing, second instruction fetching the operand, third instruction decoding the instruction, and fourth instruction um, fetching the uh, fetching the instruction from the memory. So that means different operations are takes place in a parallelly. So this is called pipelining. So this is called pipelining concept. So conflicts that occur during the instruction pipeline. So when we are when the pipelining is takes place due to some other conflicts, the pipeline process may deviate from its normal operation. So these are the conflicts encountered in the instruction pipeline. First one is the resource conflict. So these resource conflicts caused by access to the memory by 2 segments at the same time. So most of these instructions can be resolved by using a separate instruction and the data memories. So these resource conflicts means suppose if the I1, I2 are there, 2 instructions. So if the 2 instructions are trying to use the same resource, then this type of conflicts will occur. Then data dependency conflicts. So data dependency conflict is nothing but suppose if I2 is processing, then if the I2 is dependent on the values which are generated from by the I1, then such type of conflicts are called data dependency conflicts. That means the I2 is waiting for the results which are generated by the I1 instruction, first instruction. Okay, that means the I2 it cannot process its operation until the results of the I1 is available. Okay, so that is called data dependency conflicts. Then third one is branch difficulty conflicts. So these branch difficulty conflicts will arise from program control instructions that may change the value of PC. So that means the PC value, whenever the program control is transferring from one address to the new address, the value of PC will change. So due to that, this branching difficulties will occur. Next, define parallel processing. Explain the Flyn's classification of the computer. So parallel processing means executing two or more operations simultaneously. That is called parallel processing. And according to the Flyn's classification, okay, so the following are the needed to process each instruction. So these are the various steps followed in the parallel processing. First one, fetching the instruction from the memory, then decoding, calculating the effective address, fetching the operand from the memory, execute the instruction, and store the results back to the register or memory. So parallel processing. So parallel processing, it is a method to improve the computer system performance by executing two or more instructions simultaneously. So according to Michael J. Flyns, the parallel processing can be classified into mainly four types, that are SISD, that means single instruction stream, single data stream; SIMD, single instruction stream, multiple data streams; MISD, multiple instruction streams, single data stream; MIMD, multiple instruction streams and multiple data stream. So the sequence of instructions read from memory is called instruction stream. That means we are storing the program in the memory. Program is nothing but a collection of instructions. So always the instructions are fetching from the memory. So that's why the sequence of instructions that are read from the memory is called instruction stream. And next one is a data stream. So the operations performed on the data in the processor is called data stream. So this parallel processing, it may occur in instruction stream or instruction data stream, or sometimes it may happen in both, as in instruction stream as well as a data stream. So first one is a SISD, single instruction, single data stream. It represents the organizations of a single computer that contains a single control unit, single processor unit, and the memory unit. So that is this type of computer are classified as SISD. So here you can see it is having a single control unit, single processing unit, and single memory. So in the memory, we are storing a program. So program is nothing but a set of instructions. So the set of instructions are fetched from the memory. Then these are given to the control unit for to generate various control signals. Then they are given to the processing unit for further processing. Next, SIMD, single instruction stream, multiple data streams. So it represents an organization that includes many processing units under supervision of the common control unit. So here you can see we have a single common memory and a single control unit. So these are supervised by a single control unit. So we have multiple processors, multiple processor units, and multiple memory modules. Okay. So the shared memory unit must contain multiple modules so that it can communicate with all the processors simultaneously. And coming to the third one, MIST, multiple instruction stream and single data stream. So this structure, it is only for theoretical interest, but in practicality, there is no such type of systems are exist. And fourth one, MIMD, multiple instruction stream, multiple data stream. So this type of organization, it refers to the computer system capable of processing several programs at the same time, because we have the multiple processors are there. So the multiple processors, they are executing multiple programs which are read from the multiple memories. So these are the MIMD. And then illustrate the number of clock cycles that takes to process 200 tasks in a six segmental pipeline. So here we are using a six segmental pipeline concept, and the process, every process it takes 200 tasks. So in order to process 200 tasks, we need to calculate the number of clock cycles required. So since it is a six segment pipelining, the k is equal to 6 and the number of processes n is equal to 200. So the total time required is k plus n minus 1. So where k is the 6 and n is the 200. So 6 plus 200 minus 1. So that is equal to 199. So that is equal to 205. So in order to process 200 tasks in a 6 segment pipeline, we require 205 clock cycles. So in this lecture, we have discussed about various questions related to the multiprocessors. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.